with simple words. There's a reason why we have small words in the dictionary so that we can use them. So we want simple explanation. So who wants to take a stab at that? How will you explain what this weight means? So for example, what does the weight for person number 2 mean? What does it mean? Any takers?
You can also raise your hand if you want to answer verbally.
No takers? So Lungile, for every question that is not answered, you'll have to answer it.
I'll pick someone, don't worry. All right, so there's a response. Person 2 is in a smaller sample, and then there's overweight. There's person 2.
No, the first question
Population 1
is
is more.
explain what these weight values mean to your 8-year-old child. So what does it mean? Explain it in a way that your 8-year-old child can understand. What does that weight value mean? You can pick weight for example, what does the weight value of 314 for person number 2 mean? What does it mean? So again, explain it so that your 8-year-old child can understand.
Population 1 is more represented.
What does this number mean? The number 314. What does it mean intuitively? How do you explain that to an 8-year-old child? Because if we don't understand these things, we can't understand analysis of complex surveys. We need to understand it at a very, very simple level.
Person 1 represents 3.14 persons in the population, including the person 1, and person represents 314 person in the population, including the person 2.
Exactly. So that means that a weight of 314 means that this guy, number 2, stands for 314 people. It's like we wanted to send them on a mission, but the other ones couldn't go. So we said, okay, you go for us. Go for all 314 of us. So that guy is now representing them in the survey, right? So the representations are mutually exclusive. So that's why when we add up all the weights, we are going to get the total population size, right? So that's what those weight values mean intuitively. So you can now understand why weight value cannot be negative. Like, what does negative mean? Does it mean there cannot be minus something people? Count cannot be negative, and that's why you can have negative weight. So that's what that means. So be part of the question, which of these two is more likely to come from an oversampled population? Person 1 or person 2? Remember we talked about how oversampling has an impact on weight. So between person 1 and person 2, which of these is more likely to have come from an oversampled population?
Person 1 and person 2. Another says person 2.
Okay, we need an explanation. You need to defend your answer.
Adeyemi, why did you say 2? And Kenneth, why person 1? Person 1 comes from an oversampled population. Why is that? Why do you say that, Ntadi? Prof is asking for an explanation. And then there's person 2, as he represents a large number of persons.
Okay. So remember, we gave an analogy yesterday. We said, imagine you have 2 populations. Each of those populations has 10 members in it. We said, in the first case, we sampled all the people in population 1. So all 10 of them were sampled. And we agreed yesterday that since each person was sampled, they stand for themselves. So each person has a weight of 1. Sorry, we have a hand up. Somebody wants to explain to us. I think I saw a hand quickly up there.
Yeah, it was quickly lowered.
Okay, all right, that's fine.
Okay. Ntadi, where's that hand? Okay.
I believe it's Ditoka Gideon.
Tiltoka.
Okay, thank you. Can you hear me, please?
Yeah, we can hear you clearly, yes.
If I can remember, yesterday we said whenever we oversample, that the weight becomes smaller. So in that case, person will go for person 1 to be more likely to come from an oversample population.
Excellent. Very, very good. So that's the correct answer. So, and you've also established the principle in general that when you oversample, if I took all 10 people, then each person only has a weight of 1. So that means that obviously oversampling would, in general, result in smaller weights. All right. Question number 2, combining multiple enhanced cycles. So you append 3 enhanced cycles, 2009, 2011, 2013. Your goal is to increase the sample size. Now, will using the raw pooled weight adversely affect prevalence estimates, population counts, both or neither? Again, these are the fundamentals of complex or just general analysis that you need to know. So we're not trying to focus on any sophisticated or fancy stuff. What we're trying to focus down on are the bare essentials that every one of us needs to know. Because when you're doing analysis, you need to know the implications of certain actions on an estimate, the validity thereof, right? So that's why I want to make sure that we all understand this, the basic foundational elements, the theory of it, so that you don't erroneously do mistakes in your analysis. So when you're combining data from many years and you're using the weight variable, what would that adversely affect? Will that adversely affect the weight, the prevalence, population count, both or neither? What do you say?
Both. If you want to speak, please raise your hand. Okay, there's both. Anyone else?
Okay. Let's understand it from first principles. Let's understand what goes on behind your software so that you understand why certain decisions might warrant you to take certain actions. So let me open a spreadsheet here and let's look at it from first principles. Just a minute, I'm opening the spreadsheet here now. Where is this? Okay. Okay, can you see my spreadsheet, Lungley?
Yes, we can.
All right, so here's what we're saying. You have data from 2007, and here you have you have 1, 2, 3. So let's say the survey has 3 people in it. Let's keep it simple. And these individuals, their weights are 5. So let's say keep it 5, 5, 5, right? And then you take 2000 let's say 8 data. And this one also individuals 1, 2, 3. Their weights are 5, 5, 5. And then let's look at the third case, 2009. Individuals 1, 2, and 3. Again, their weights are 5, 5, 5. Now, if you recall, we said if you add up all the weight, what do you get? What does that give you? So now let's pull the data sets together, right? We have data sets here. This is from 2008, 2007, 2008. So this is the years here. Let me move it to the side. So 2007, 2008. So this is your appended data set, which you have combined to increase your sample size. We need to understand what goes on behind the scenes, right? 2009. So now instead of having 3 people in our data set for analysis, we have 9 people. So we need to understand what's happening. And so remember we said that the prevalence estimate is simply equal to, so let's say this individual here reported values of 1. This was their responses, 1, 1, 1, 1. Right? So if we took the prevalence in the individual years, 1, 1, 1, right? This is equal to, remember we said 5 times 1 plus 5 times 1 plus 5 times 1, which is equal to 15 divided by 3, right? If you get lost at any point, let me know. I'm trying to make sure we take it very, very simple. Now, let's take a step back. So remember we said that in the complex survey, the sum of the weight equals what? Let's start from there. I think that's an easier way to start from. The sum of the weight in each year gives you what? Who remembers? So if we add 5 plus 5 plus 5, this is equal to 15. This 15 represents what?
It's total population.
Exactly. So if, for example, if our survey, NHANES survey, is a survey of all US adults, we might get a number like some 200, 3 or 300 million, whatever that number is, right? That is the total population size. But now, when you now pull your data together, and remember, if we analyze the data in each year separately, we will have gotten this population size more or less the same, 15, 15, 15. But now when we pull the data, we get something else, right? We get a total population size as this. And then you say, oh, the population of America is 45. But no, it's not 45, it's 15, right? And so that's the danger that comes from pulling data. You get an inflated number of the population count size because the sum of the weight equals to that population size. And so the solution to this is that when you pull data like this, you have to rescale the weight. So take note that pulling data set together has no impact on the prevalence estimates, right? Whether you pull the weights together, remember that all the weights are increasing by the same factor, right? In this case, when we pull the weights together, they're increasing by a constant factor. So it doesn't really affect the point estimates. But it affects the population count because we are adding across the pool data. And so that's why whenever we pull data like this, we must rescale the weight by dividing the weight variable by the number of cycles. So here, this was the old weight, and we have to get a new weight by saying this is equal to this divided by 3. Because why 3? Because we pulled data from 3 years, 2007, 2008, 2009, right? So that is what we have to do. And such that when we now add this together, it gives us 15, which is the correct answer for the population size, right? So when you pull data across multiple years, if you are not interested in generated weighted counts, you don't have to do anything. However, if you are interested in generating population count in addition to prevalence, then you must rescale your weight by dividing the weight variable by the total number of cycles appended together. I hope that's very clear. Any questions on that before we go to the next item? And if it's clear, give me a thumbs up. Why are we so quiet today? Are there any thumbs up? Okay. All right. Super. Thank you. All right. Let's go back to the other questions. So now let's answer this question again. So you append 3 NHANES cycles, 2009, 2011, and 2013. Will using the raw pooled estimates adversely affect prevalence estimates? No, it will not affect prevalence estimate. Will it affect the population count? Absolutely, yes, it would, right? And so we can rescale the weight by dividing the old weight variable, by the total number of cycles we've appended. But again, we only need to worry about that if we are planning to generate weighted counts. If we're not planning to do that, then we don't have to do anything. All right, question number 3. Choosing the correct weight. So yesterday we talked about the umbrella analogy, right? So we said, always go to where's the picture now? We said, always go to the picture with always go to the image or the umbrella with the fewest number of people. Remember, that's what we said yesterday. And because the umbrella sizes are fixed, right? Meaning that if you add all the weights, if you add interview weight and MEC weight, the same population size. So it's fixed in that sense. That's why we say just go to the umbrella with the fewer number of people because it's cozy and comfy, right? That's just a way to help you remember. So here you have umbrella A has 10,000 people. So you merge data from the, let's say, demographic data set, which has the interview weight, and the periodontal file, which has exam weight. And your outcome is prevalence of periodontitis. Should you use the interview weight or should you use the exam weight? Which should you use? Remember that there were 3,000 people who underwent an exam compared to 10,000 people who were interviewed. So you can see that the umbrella with the smaller number of people is umbrella B, the exam. So we should all be comfortable with this question, right? So which weight, but I'm not going to assume, I want an answer. So which weight should you use? Should you use the interview weight or the exam weight?
Exam weight, B.
Okay, is there any person who said interview weight? Because they have to explain themselves very well now.
No.
Okay, all right, that's good. All right, this is easy. The enhanced file come as XPT files. So yesterday we talked about how to download them. They are machine readable files. So please do not save them as text files. If you're reading them on the Chi-Squares platform, you don't have to do anything special. The Chi-Squares platform allows you to read data from any format. So you don't have to do anything special. You should absolutely try recording variables and see. So this is something we did yesterday. We won't repeat it, obviously, because for time considerations. All right, survey mode settings. The instruction was for you to set your data set to survey mode by specifying the weight variable, the PSU, and the strata. Why must all three variables be included? Any responses? This session is supposed to be an interactive session. It's homework, so it's just trying to solve the questions from homework. So it's interactive. So please don't leave me hanging. So what happens? Why must you all include all three? If I'm feeling late.
Account for complex design.
Okay, it's excellent. And so account for complex design. So you have to include all three. Is it all surveys that will have all three? Because again, our focus is not just on NHANES, right? This session is really just using NHANES as a poster child for complex survey data. So it's not enough for us to just know about NHANES. We need to know the principles, right? And that's the fundamental difference between principles and any specific regulation or law or policy, right? Because principles are very broad. So it allows us to know things very broadly. So the question is it every survey that will have all three, weight, PSU, or stratum? And can you think of a scenario where you might not necessarily have one of those three? Because when somebody describes a study design to you, or when you're designing a complex survey, you should just know upfront, oh, I don't expect to have this, or I don't expect to have that. So in what settings, for example, might you not have PSUs? So think.
If you don't stratify.
Okay. But PSU is not about strata, right? PSU is clusters. PSUs deal with clusters. Strata deals with strata. So stratification, as the name implies, deals with strata. So the variable stratum or strata has to do with stratification, whereas the variable PSU has to do with clusters. So in what scenario might you not have cluster PSU variable? Because remember, on the KNHANES platform, you have those three boxes where you need to select. So the goal is that as methodologists, we all are methodologists. By being in this class, you're all methodologists. Just by looking at it or reading a study design, you should be able to tell that, well, this survey will not have a PSU variable. I don't need anybody to tell me because the design is obvious that it doesn't have a PSU. So can you paint a scenario of a situation where you won't have a PSU variable or where you will not have a stratum variable and you may have a weight and the other one, for example? Because you can have one, two, or all three of them, or none of them.
Simple random sampling.
So
Census.
sampling will give you what? Will you have all, none, one, two, or three?
If the sample isn't supposed to be representative of the population due to the sampling method used.
Okay.
In SRS, we don't have all three.
Okay. So simple random sample, right? So in this case, let's say that I come to a country, let's say I'm doing a survey in let's say Zamunda, right? A hypothetical country. And I go to the Department of the mail agency, the Department of Communications. The communications department has everybody's phone numbers or has everybody's email address or has everybody's phone number. And I said, hey, I want to do a national survey for the government. Can you allow me to draw a random sample, a simple random sample from your database? So in this case, since I'm sending the surveys via, digitally, it doesn't really matter. The issue of logistics doesn't really apply here because I can easily do that. I just have to write some program that will, disseminate the survey to everybody on their digital phone. So I draw a random sample of 2,000 from the 1 million inhabitants of Zamunda, and they all get the survey and they all do the survey. So in this case, I use simple random sample. So simple random sample assures that everyone has an equal probability of selection. So in this case, I don't need weight. Why? Because everybody has an equal probability of selection. I didn't use cluster sampling, so there won't be PSUs. And I didn't stratify, so there won't be strata. So in this case, if I get my data, all I just need to do is just take the data and just analyze it. No extra work, and that's easy peasy, right? So that's a scenario where we will have no PSU, no stratum, no weight. All right. What of a scenario where we have, let's say, weight and maybe strata, but not PSU? Who can describe a scenario like that? Because remember that survey design is both a science and an art. So you need to be able to design a study accordingly based on the resources you have on ground and based on many other considerations. So who can give us a description of a scenario where you might have weight and let's say strata, but not necessarily PSUs? And you can choose to modify the example, the illustration I gave. how will you modify that hypothetical scenario to give you a design where you had a weight variable and a stratum variable, but not a cluster, so you don't have PSUs? Any takers? This is why you should do your homework. All right, Lunge, as usual, if nobody answers, you have to answer the question. We have no hands up? Please, somebody should attempt. It's there's no aha, good. I see a hand up.
Ali? We can't hear you if you're speaking.
Ali, are you on mute? For whatever reason, we can't hear.
No.
Okay, it's not on mute. All right. All right, maybe somebody else will have to take Ali's position. We need somebody to give us an idea or their own idea of how. Again, we're all methodologists here, okay? Don't be shy.
Someone says conducting surveys among senior high school students.
No, I want you to modify the illustration we're giving, right? You are now in Zamunda. So if you're conducting survey among high school students, like the devil is in the details. So you have to tell us how will you design the study in such a way that it will require weights and strata, but not clusters or PSUs. These things we have to make sure they're not just technical terms in our ears, that we need to understand them to the basics. And we need to understand them in the context of, oh, okay, I'm designing a study. How do I want to do it? So how do I want to do it so that I will have this or that, right? That's the goal of this 2-day seminar. It's not just saying, oh, we want to analyze and we just want to grab enhanced data and analyze it and move on. No, the goal is you have to understand the principles of study design, which includes the design of studies. So it's not just taking the data set and analyzing it, but if you were to design it, how will you do it? So those decisions that are made at the design phase are very important because that's what really makes you a methodologist. So how will you design a study that will have a weight and stratum, but not clusters? You can use the last case and build on it. Okay, there are no takers, I'll just have to describe it. But I would really love someone to take a shot at it.
Sure, can I try?
Please, thank you very much.
So I believe that to even have a cluster, a cluster is needed when you don't have a master list that is representative of the population. So in that example you gave us, you already told us that when you came to the country, you asked them for like a list or something, then they give you about 1 million people, which is like their population, of which you now random sample to get your sample. So what you asked us is an illustration where we can use weights and strata without clustering. So I would say that weights, okay, so say for example, let's say you're doing it across demographics, for example, and maybe you want to okay, I don't know how to put it, but let's say the older people in the population, maybe they are of a smaller number compared to, let's say, middle-aged and younger people, for example, and you want your study is supposed to be how do I put it down? You're supposed to like account for that imbalance in the demographic. So that will be where you use your weights, for example. where the older demographic will be weighted more than the younger ones. Then I think for the strata, using a strata in this scenario you gave us would be okay, I can't, I'm trying to think of how you use a strata in this scenario you gave us. Can't really.
Okay. You've done excellently well. So let me just so let's push towards the final line. But you've already said it, right? So and that is very beautifully said, right? So let's establish some things that if this is the only thing we take home, then we've taken enough from the class, right? Lesson number 1, we only use weights when the selection probabilities are blank. What's the blank? That's a very, very key word we want to remember. If selection probabilities are blank, then weights are needed. What's blank? It starts with the letter U.
Unknown.
Not equal.
Unknown.
Unequal. So unequal, that's a key word there. So let's etch that into our minds, right? If selection probabilities are equal, we don't need weights, at least not design weights, right? Design weights are required to correct for unequal selection probabilities, right? So if we did, so if we did any sampling method that everybody has an equal chance of selection, then weights are not needed. Now let's build on the response that was given. We come to Zamunda and we said, oh, we're interested in looking at it, let's say prevalence of falls, like to fall and break your hip. And remember, whenever we want to, like this is an issue that we intuitively we know that this is something that will affect older adults. And we also know that there are not so many older adults in the country. So we're like, okay, it's very important for us to make sure that we design a study in such a way that we capture sufficient number of older people in this study. So we need to stratify, right? So first decision we've made is now, should we stratify or should we not stratify? Now, that decision is based on, well, do we really need to stratify, right? And the factors that would make you know whether you really need to stratify are, 1, is it hard for us to access, all the populations of interest? So in this case, we're interested in older people, right? Is it hard for us to access them? Well, maybe yes, in this case, because there are very few of them. And so if we just left it to chance, we may not be able to get them in sufficient numbers. And they are a very key demographic that is very, very related to the research question. So we don't just stratify on anything and everything. We stratify on only things that are highly correlated with the outcome of interest. In this case, the outcome of interest is falling and breaking your hip. Of course, that is highly correlated with age, right? So it's important for us to then ensure that our study has sufficient representation of older people. So that's the decision number 1. The decision number 2, do we have a way of actually accessing those people if we stratified? So in this case, we spoke to the guys in the communication. They said, oh, well, we have some landlines here, and the landlines, people who are older are more likely to have landlines. So we choose to say, all right, we're going to first of all stratify the sample by landline owners and cell phone owners. We know that, maybe the older people are more likely to use landlines. So we said, all right, we'll stratify, and then within those strata, we're going to do a simple random sample, right? So you can see here now that we said, all right, we stratified. I said the sampling fraction for the older people will be higher to make sure that there are enough of them in the study. So we stratified. 1, we gave a higher share of a sampling to the older people to make sure that they are amply represented in the sample. And just by doing that, now the selection probabilities are not equal because the older people have a higher probability of being selected than the younger people, right? So in this case, we created strata, so we need stratification, and we have created a scenario where the sampling probabilities are unequal across the strata, right? So we have to adjust for that. But we did not use cluster sampling. Remember, within each of the strata, we just drew a simple random sample within each stratum. So in this case, there is no clustering, but there is stratification and there are unequal selection probabilities. So as the last person very eloquently said, that represents a scenario where we have need for stratum variable and a weight variable, but we don't have a PSU variable because PSU, primary sampling unit, applies to clusters. So if you design your study that way, you should obviously know immediately that, oh, when I create the final data set for analysis, this is what will be here, this will be here, but this will not be there. And I can explain in my documentation why that is the case. I hope we're good. I see there's a hand up. I'm not sure if that's a question or if they want to contribute to
Yes,
this.
yes, Prof. It's a question.
Okay.
I get confused with a bit of the terminology, so I just want to give an example. Maybe
Okay.
that may help to clarify my doubt.
Okay.
So assuming that, let's say I have a class of students made up of different races, let's say white, black, Hispanic in the class. I take blood samples from them. I want to look at their blood glucose levels. So, and then I want to compare whether the white guys, the black glucose levels are higher than the blacks.
Mhm.
In that case, will I need to apply my sample width?
So the first question we're going to ask you is are you sampling in a way that so the sampling method drives the methodology, right? Form follows
Okay.
function, right? That's the fundamental rule of design in any context, whether it's engineering or study design, that form must follow function. There's a reason why cars have wheels and not legs. Sure, somebody could create a car that has legs, but that would be an awfully slow car, right? So the function of anything drives how it looks. The same thing applies with study design, right? Whether the survey has weight, which is how it looks, is a function of how it functions, of how we design it. So in this case, the issue of whether the survey has weight or not is a function of how did you design it? How is it functioning? Like, did you draw a simple random sample? In that case, then everyone has an equal probability of selection. And so there's no need for weight. Why? Because weights are simply the inverse of the probability of selection. So if the probability of selection is, let's say, 0.2, 1 over 0.2 equals the weight, and everybody has the same weight. If everybody has the same weight, we call that a self-weighting sample. In other words, we don't need weight, right? So your research question would be, the answer is a function of, did you sample in a way that the selection probabilities were unequal? So let's say you might have chosen in your class, and if it's just a simple class, you may have just taken the whole census, like you interviewed everybody in the class. So in that case, that's not even the sample. So we're not even worried about issues of sampling because that does not apply. So for sampling to take effect, there has to be some element of randomness there. So if we took everybody in the class, well, we have saved ourselves the headache of having this discussion about selection probabilities because that does not apply because everyone was selected. There was no probabilities involved. It was a certainty that everybody was selected. Now, if it's a very large class, yeah, go ahead, please. Yes.
Yes. So, what if, let's say, I'm not the one who have done the sampling, someone else did the sampling. The person has reported that there are sample widths for each of these. How do you call it? Each of these structures. But in my case, I'm not going to combine them. I'm trying to make a comparison. Will I then apply the width, and how do I apply the width?
The fact that you're making a comparison doesn't necessarily mean that you need weight. You could have just done a simple random sample and you can still compare within that sample, right? So like everybody in this class now, I can just, give you a survey and compare your results. And I can still compare without having had to draw a sample. So comparison doesn't necessarily mean that you have to draw unequal samples, right? So we should know when, like in the case when we want to compare, right? You should know when to stratify. If I want to, in general, statistically, we want to make sure that there's power in the comparison. And statistical power is a function of a smaller group. If I have two groups and there are 100 people in one group, and there is only one person in the other group. Well, the fact that my sample size is 101 does not matter. The fact that I have 100 people in the other group does not matter. Statistical power is driven by the smaller group, right? So in a case where I see that, if I just were to do a simple random sample, I will end up in a scenario just because of the law of large numbers. This big group would be the most of the sample, and this tiny group will just be one person or two people. Clearly, I can't compare in that context. So I'm like, what do I do? Well, I'm going to stratify. I'm going to stratify and give a bigger share of a sample to the smaller group to make sure that there are enough people in the sample so I can compare. Those are the thought processes that should be going on in your mind before you design the study, right? It's not after you design the study and then you're like, oh my geez, like I don't have enough people. No, that's medicine after death. This is why we always emphasize study design. At the very beginning, you should say, I want to make comparisons. And I know that statistical power is driven by the smaller group. And I know that if I left this to chance, I may not have enough people there. So it's clear to me that I need to stratify. And so I'm going to stratify. I'm going to take 5% of these people in this group, but I will take 20% of the people in that group, that small group. So right away, you know that, oh, these people have 5% of the sampling fraction. The other one have 20%. Now, sampling probabilities are unequal. 5 is not the same thing as 20, obviously. And so this tells you that, okay, you need to use weight. So the point I'm trying to say is that the issue of weight or no weight is a function of study design. And there are things that, and that's why we're taking this time to go over these issues carefully so that you are well empowered to think about these things carefully right from the moment you're designing your study. It's not after you've collected your data that you're having these discussions. It's before you even put paper to pen to say, I want to create questionnaires. These discussions have to happen way before then so that when you collect your data, everything is fit for use. I hope that answers your question.
Yes, Prof. Thank you.
All right, great. All right. So what about a scenario where we have weight and let's say cluster PSUs, but not strata? Who can give us an example of that scenario? We have weight and strata, but not weights and clusters, but not strata. We need another brave volunteer to assist us.
If we only have first stage sampling.
Sorry?
If we only have first stage sampling.
Okay. Okay, we need more elaboration than that. The devil is in the details, right?
Ali, you may speak. Oh, Ali has a mic issue, I think.
All right, we need a brave volunteer. Guys, this is a methodology class. I can't be the only one talking. So, in methodology classes, we talk and we argue and we provide evidence. So, please, when can we have weights and let's say PSUs, but not strata? What scenario can you think about? England, I just have to call you now.
Peter to my rescue. Conducting survey among senior high students who has ever used drugs in studying.
Okay, the subject matter itself is immaterial. So I want us to establish that, right? The study design in this case is like the topic in of itself is not of like this is a methodology class, so we're not really interested in the topic itself, but in the execution of the methodology for that topic. So how will you sample for that topic that is titled drug use that will lend itself to a design where you have weight and PSUs, but not necessarily strata. Again, okay, let's take a step back. What problem are we solving with stratification? Because we have to start from first principles, right? We're always trying to solve a problem. So if there's no problem, we'll have to solve it. So what problem are we trying to solve with strata?
Exclusion.
Okay, exclusion. Yeah, so we have a population where we are interested in making comparisons. That's where we start, right? It's like we always drive the show. We are the ones driving the show. It's not some unknown forces or some literature review or what other people are doing. No. It's what we as investigators, as methodologists are interested in that drives the design. So here we're saying, oh, I'm interested in making comparisons between these groups, and I see that these groups are not uneven. But if I'm not interested in making comparisons in the first place, if all I'm interested is in just overall prevalence and maybe among key subgroups, or I'm interested in making some comparisons, but the groups are adequately large, obviously there's no need for stratification in this case. So let's build on that example that the other individual mentioned. I'm interested in doing a survey of students about drug use, right? And for efficiency, well, where are students found? Students are found in schools. So I decided, okay, I don't have a list of all the students. And even if I do, students don't have telephones. They don't have maybe their parents. Yeah, for whatever reason, that's the only way to contact them is in person. So I said, okay, I'm going to sample schools. So I draw a random sample of schools and I go to those schools. And then I select students and I interview them and I get my data. In this case, there's no stratification because I didn't say, oh, I'm going to divide the population first into schools in rural areas and schools in urban areas. And then I'm going to select the rural and then the urban for whatever reason, because that's not my hypothesis. I don't care about rural or urban because that's not of interest in my study. I just selected from the Ministry of Education's list of schools. I selected, schools, and then I sampled accordingly. So in that kind of case, I will end up with PSUs because I use clusters, right? Now, not every use of clusters will result in weight, but sometimes we select certain clusters in weights in ways that result in unequal selection probabilities, right? So, the use of cluster sampling is not a one size fits all. It's, we can spend a whole day talking about cluster sampling. But the bottom line of what we're trying to say is that if we use a sampling method, in this case, cluster sampling, that ensures or that makes it clear that the selection probabilities are unequal, then now we have to worry about clusters and unequal selection probabilities. So we'll have both weights and PSUs. But since we did not stratify, we will not have to worry about strata. So the moral of the story is that it's not enough for us to just grab a data set from the website and just analyze. We all, as researchers, as methodologists, need to be aware of design decisions, and we need to be able to design studies that will be able to capture those nuance, right? So that's why we're going through. That's why this homework was set up, so that we have that expertise to do that. All right, now narrow confidence intervals. So the question 7, we all want narrow confidence intervals, but what happens if narrow CIs are illegitimately obtained by ignoring survey design? So remember we said there are 3 variables: weight, PSU, strata. The weight focuses on the point estimate, and the strata and the PSUs affect the confidence intervals. So when you ignore the PSU and strata, remember we said the confidence intervals become narrow, right? If you have cluster sampling, let's say you sampled people in clusters and you do not account for the PSUs, what will you expect to happen to your confidence intervals? Will it be narrower or will it be wider? And why? So you've done cluster sampling within schools. So you have cluster variable, and you somehow did not know that you're supposed to capture these clusters, right, in your data sets and account for them. And you end up, creating prevalence estimates with confidence intervals. The question is, will the confidence intervals from those estimates be wider or narrower than had you accounted for the PSUs? What are your thoughts? Narrower or wider?
There's narrower due to same information. Narrower again.
Okay. All right, can somebody explain to us why they'll be narrower? It's the same information, but can you explain on that a little bit so that those who are not fully following me understand?
Hasi, would you like to speak? Ibrahim, can I unmute?
Yes, the confidence interval when we account for PSU and stratas, we widen the confidence, it will widen because we are accounting for the variations in other clusters. But if we only account for just focusing on only one cluster without looking at other clusters, the confidence interval will be narrower. But when we expand and consider other clusters, due to their variations, the confidence intervals will widen. That's my perspective.
Thank you very much. I think we have another hand up, Courage.
Yeah, hello. Okay, so I think that because within a cluster, people tend to be more similar. So the answers that they give would seem to give the confidence interval a more narrower one than when the cluster is acknowledged in the system. That's if it's put into consideration, it's able to tell that, okay, these people are within a cluster, and there is that tendency of similarity in their response. So the outputs will be given a broader confidence interval.
That's very excellent. Thank you very much. So you're all correct. So that I think okay, good. It says, what statistical danger does this create? I think we've mentioned it, but what's the statistical danger in artificially narrow confidence intervals? I mean, we want narrow confidence intervals, but when they are illegitimately obtained, that's an interesting choice of word, but I loved it. That creates a scenario, right? We have a problem. So what's the statistical danger? Is it type 1 error or type 2 error that we're afraid of here?
Type 1.
Type 1, good. And what's type 1 error? So that those at the back can hear very well.
False positive. False positive effect.
Very good, which means what?
We are overestimating.
Okay, overestimating. Okay, well, how else can we describe it?
Rejecting like true. True hypothesis.
Okay.
True null hypothesis.
Okay. Can we use simple words so that everyone can understand? Can we say it in as simple a way as possible so that an 8-year-old child can understand, or at least my grandmother can understand? What does it mean?
Means we are getting significant where there's no significance.
Exactly. We say that, something is there when nothing is there, right? And again, remember that confidence intervals, when they overlap, that might suggest that results are, non-significant. But if your narrow confidence intervals are very narrow, that means that they're not likely to overlap, which means that you're very likely to end up saying, oh, well, they're very different, which means that you're very likely to end up with a type 1 error. So you see how that cascades. So that's why we are worried about issues of PSU right from the beginning, because we know that it spirals downhill to when we declare that, oh, we have significance, but you don't. You have stolen the significance by failing to account for PSU. So that's why we are interested in all of these things, right? So our class on NHANES is not just about just analysis, but we all need to have a very solid grounding in methodology, right? And I don't necessarily mean the fancy stuff in methodology or the complicated stuff, the basics. And all of these things are part of just the basics, right? So please, we need to understand these things to their core, because obviously they have an impact on how we design studies. All right, that's all of the homework. We took a lot of time, 1 hour approximately, to go over that because they're very important, right? It is the basis. If that's the only thing we get from today, that's important, because as people who design studies, we need to understand this elements. Any questions on those before we leave? Any questions?
Courage.
Okay, please. I want to make this analogy and see. I did a study on looking at drivers of mortality using a data set from our surveillance system. That is the inpatient cases that are captured within a region. And we did realize that, as we mentioned, I used the survey design to do it, but I used the PSU and then the stratification to account for clustering within the facility. But we didn't use any weight because we use the sensors of the data. I want to know how correct that would be in this context, or because should I have used a weight? We use the sensors because we thought all the eligible population in this was having equal of selection. So we did not use any weights, but we just used the PSU and then the structure. Will it be a correct method, or would there be a different approach to it?
All right, thanks. All right, I want someone to critique that approach. And just to put it in very simple terms, they did a survey. Well, they did a data collection. They took a census, which is everybody. He says that they didn't have weight, but they had clusters and strata. I need someone to critique that.
Because actually the data was an existing data.
Yeah.
That's the inpatient data that was captured in the facilities, in the hospitals.
Yeah, well understood. Yeah, thank you very much. Yeah. So is there a fallacy, or is there a loophole in that narrative that anyone wants to critique? Please, don't take any critique personal. This is a methodology class, so please, I hope you don't. This is just for learning purposes. All right. So anyone wants to share their thoughts on that? No one. This is why are you guys so shy today? Okay. Lungley, I saw your hand up.
Peter says if it's a census, there would be no need for waiting.
But if it's a census, you have an argument further, right? If there's no census, what else would there be no need?
Riri, please mute.
There won't be a master list.
There won't be master list. Yeah, but so in the argument, in the case study presented, it was said that this data collection from existing data had no weight, but had clusters and strata, but at the same time was a census. I need someone to critique this. So cluster, okay, let's break it down. Clusters, all right, Ilya, please go ahead.
Is it possible?
Okay, I would say clusters and strata apply only when we are sampling. Since it's a sensor, we shouldn't have any of those.
Exactly. That's the simple answer. Strata, clusters are all ways of sampling. Sample. A sample means a part of the whole. But the case study presenter said that they took the whole. If they took the whole, then we won't have weight, we won't have clusters, we won't have strata, because they took the whole. Now, in the analysis, what also won't we have? We've been talking about prevalence point estimates and confidence intervals. When we're analyzing the data from that census, what would we not have?
Okay, I think we'll work with just population statistics. We will not have point estimates because we're not making an inference from a sample since we're using the whole population.
Okay, can you reverse your answer the other way around? We'll have point estimates, but we won't have what? Point estimates means things like percentages or means, right? So we will surely have those, but what won't we have? Since it's a census.
Confidence interval.
Excellent. And why won't we have confidence intervals? Why wouldn't it make mathematical sense to have confidence intervals?
We use
because
the population.
You need to have repeated sampling of the population to have confidence intervals.
Yeah. So sampling error is a mathematical basis for calculating confidence intervals. If there was no sampling, then we can have sampling error. And if there's no sampling error, there can't be confidence intervals because it doesn't apply mathematically. So in this case, when you generate your estimate, it will just be point estimates, right? The issue of confidence intervals will not apply. So that was a great, case study to just highlight that we only have to worry about sample size, sampling, clusters, strata, or all of those things when we are sampling. But when there's no sampling occurring, meaning when we're taking the whole census, none of those things apply because it's a census. It's the whole thing we're taking, not a sample. I hope that's clear. So thank you very much for bringing that case study. Yes, Courage.
Yeah, hello, Prof.
Yes.
So it's actually a condition which we say is an acute condition that we were looking at, and it was taking over a period. So we were expecting that there are some people who may even repeatedly get infected, come back to the facility. The same clinician may be attending to them. And we are looking at the outcomes being similar within that facility. That's why we chose to use the clustering. So I don't know in that scenario, because we took it over some period, and it's expected that there will be some people coming back in the facility on the admission and all that. So I don't know if that one will account different.
Well, that's a very good point. So in this case, what the unit of analysis is what? Because you've created a scenario where folks are coming to hospital, right? When you're doing analysis, the very first question you need to ask yourself is, what is my unit of analysis? In this case, there are two options. The unit of analysis could be the individual, or the unit of analysis could be the visit. Which is it in your use case? What do you think makes most logical sense? Is it the visit, or is it the individual? What do you think?
Well, we use the number of visits.
Excellent.
We use the visits.
That's a great choice, right? So the visits are that means that in your spreadsheet, you're going to have, where's my spreadsheet now? All right, so in my spreadsheet, I'm going to have like, each row is a visit, right? So visit 1, visit 2. So this, so I may have, as variable name of individual, the diagnosis, and all of that, right? But now you've raised an important point that in this case, this guy number 1, let's call him Alex, visited the hospital here and here. So we have Alex coming to the hospital multiple times, right? Now, when we do analysis, one of the assumptions in many analysis that we do is the assumption of independence. That means that row number 1 is not related to the row number 2. In this case, that's obviously not the case, right? Because Alex has multiple visits. The unit of analysis is the visits. And in as much as we have multiple visits from the same individual, we can see that the observations or the records from him are going to be correlated. So let's say Alex loves eating donuts. So in this case, he's like, okay, visit 1, did he eat donuts? Yes. Did he eat donuts? Yes. Of course, like they're going to be correlated because this guy loves donuts. So that observation, you'll see that it's highly correlated with the same person. Now that, Courage raised a point, right? So accounting for clustering. So in this case, the clustering we're talking about here is quite different from clustering or cluster sampling. Different things have the same name. So here with cluster sampling, we're saying how do we select individuals from a population within groups. Here we're saying that how do we account for correlation within this analysis because their observations are clustered, right? And there are many ways to do that, statistically. We run into the same problem when we do, case control studies because the cases, you might have a case and then you are matching them to controls. So, so control 1, control 2, control 3 are linked to case number 1. Obviously, they're not independent, right? So that's the same issue that you Courage just raised here. And in all of these scenarios, we have to account for the clustering in the data set, and there are different ways. In this case, for example, we use a conditional logistic regression, and that's the reason why we also have a mixed effect model. Mixed effect because we have to worry about the mean estimates or the point estimates, but also have to worry about the random effect, which is just the source of correlation, right? So Courage, yes, you're absolutely right that in this case, you absolutely did the right thing to account for clustering. But the take-home message that we want to emphasize is that there's a difference between accounting for clustering in your analysis versus clustered sampling. Very different things. So I hope we don't get confused by that. All right, next question. Is there another question?
Yes. Chinedu, would you like to speak? Okay.
Hello, Prof.
Yes.
Okay, thank you very much for your efforts. I really appreciate it. Please, I'm conducting a study and I have to deal with the academic performance of students in a primary school. I'm taking only primary 6 in a state. I'm taking only primary 6. I want to measure the academic performance. So I use systematic sampling to select the schools within that state that are in primary. Then I'm conducting a survey. I'm giving out a questionnaire to those in primary 6 for the schools I've selected or I've sampled. So will I need to apply weights or PSU and strategy?
So if you said you use systematic sampling, which allows like every nth element, right?
Yes.
But then in this case, we in this case you seem to be using a multi-stage sampling where you first select individuals from the schools, and then within the schools you select students from the classes. So it's possible that they may have in the 6th grade, you might have multiple classrooms of 6th graders, right? So the question is, how are you selecting individuals? if, for example, you say, all right, I select every sixth school, that means everybody has an equal, all the schools have an equal probability of selection because probability is 1/6, right? And then in the second stage, you say, well, and then within the second stage, I randomly select, or I take a census of all the schools, all the sixth graders, right? Or I randomly select one class and sample everybody there. It's in that case, then everybody also has an equal selection, probability of selection, right? But if you somehow use another selection, another selection method, let's say you use, PPS, right? Probability proportional to size. Well, in that case, people in big classrooms have more likelihood of being selected than those in tiny classrooms. So the devil is in the details, right? We can't know whether weights are needed or not just by the topic. We need to know how all it is. Like in this case, in the multiple stages, how did you select? Like, was the selection of probability of selection equal in all the stages? So it has to be equal at all stages for you to say that, yeah, the probability is equal. If it was equal in the first stage but not equal in the second stage, well, then that means that you have to worry about weight, right? That's why the sampling technique on the chi-square platform uses a two-stage PPS. Let me demonstrate what that means quickly. The two-stage PPS allows you, it's a cluster sampling, but it's a very clever technique because it still gives you an equal probability sample. Let me see if I can log in. Okay, let's see. So let me show you the two-stage PPS and explain how that works. All right, so let me go to sampling here. And so let's say that I want to do so let's say you said your surveys in, okay, let's load the countries. All right. So you say your surveys in Nigeria, and you want to select it. Are there particular states that you wish to that are involved, or just one state? All right. Are you still there, Chinedu? All right. Well, let's say that the survey involves.
Sorry, Chinedu, you can unmute. All right, continue, please, Prof.
All right, sure. So let's say your survey is not necessarily national. Let's say it's in the one part of the country. Let's say there are specific states. Let's say you're studying cut across 4 states in the country. Let's say in Abia State, in Akwa Ibom, in Bauchi, and in, let's say, Bayelsa, right? And let's say that this tells you that you have from these 4 selected states, there are 76 clusters you can select from. We use clusters in this case as the second administrative unit. In the US, for example, we have states as the first administrative unit, and then we have counties as the second administrative unit. So in this case, the equivalent of counties is what is considered a cluster with this setup. So in this case, in the case of Nigeria, that will be, for example, local government areas. So this is telling you that across the 4, there are 76 clusters you can select from. So let's say in your design, you said, oh, okay, I have only resources to go to, let's say, 15 of those, or maybe even 10. That's a lot of, resources. Going to 10 local governments can become quite intensive. So you say, well, I'm going to go to 10 local government areas or clusters, and that my sample size is, let's say, 1,500 students. And you click on Get Sample. So the platform takes that information and applies a 2-stage PPS sample. Now, that's one of the most beautiful designs in epidemiology because it's so efficient. A two-stage PPS says that, well, we want to use a PPS, but we want to use it in a way that gives us a self-weighting sample where everybody has exactly the same weight, right? That's what a two-stage PPS is saying. And as the name implies, it's a two-stage. In the first stage, we select the counties or the local government areas or clusters with probability of selection proportional to their sizes. What does that mean? It means that the larger clusters are more likely to be selected in the first stage than in the second stage. So when we look at so in this case, these probabilities are so small that everything's less than 0.01. But anyway, so in the two-stage PPS, first stage, we select the clusters. Second stage, we select people in the clusters. So in the first stage, when we're selecting the clusters, we select such that bigger clusters have more likelihood of being selected. So you can see that in that first stage, the bigger clusters have an advantage. However, in the second stage, and this is very critical, we must select the exact same number of people in all the clusters we selected in the first stage. That means that the probability of selection is now higher in the smaller clusters. Let me illustrate here with our spreadsheet again. So let's say that we have two clusters. One has 3,000 people, the other one has 300 people, the other one has 30 people, right? This is the clusters. And remember, in the two-stage PPS, you must select the exact same number of people in each cluster. So let's say in the second stage, we selected 10 people here, 10 people here, and 10 people here, as is the requirement for a two-stage PPS. Now, what does that mean? What is the probability of selection? In this means that here, this is 10 over this. So you see that, right? Here, the probability of selection now suddenly favors the smaller. The smaller guy now has an advantage in the second stage. Because since we are selecting the exact fixed number of people from each cluster in the second stage. So this is the beauty of a two-stage PPS. It's like magic. In the first stage, we favor the bigger clusters. They have higher probability of selection. In the second stage, since we are selecting the fixed number of people from each cluster, it means inherently that the smaller clusters have a higher probability of selection. So big clusters favored in the first stage, small clusters favored in the second stage. That evens things out. And a two-stage PPS will always give you a self-weighting sample where everybody has the same probability of selection. It's like magic, right? And that's what, that's what's implemented on the KNHANES platform, right? So when you draw a sample with a two-stage PPS, in this case, this were the states we selected across 3 states. And this is telling us that, okay, these are where we have to go to sample in a way that is representative of those 3 states we selected. If it's a national sample, if our survey is national, we don't have to select state, obviously. We simply just indicate the country we want, whether it's the same country or any other country, and we'll specify, the number of people. In this case, this is telling us that we have 775 clusters. And let's say we want to select 30 of those. And our sample size is maybe still the same. Once we apply that, now, of course, the selection will now be different, right? But again, the two-stage PPS is a go-to for, in terms of the simplicity. It allows you to be able to generate a representative sample in a way that is intuitive without having to worry about, weight, because it always ends in a self-weighting sample. All right. Any other questions?
Okay, I'm just going through. If you have any questions, please post them. And if you posted earlier, kindly post them again on the chat box. And you're also welcome to raise your hands if you have any other questions.
So since we prioritize the homework and just going through the philosophical aspects of study design, we obviously won't be able to go through that manuscript today, but that's fine. We'll just defer it to another session where we'll, I think we've had that in the past, but we'll have a dedicated session for that. But today we'll just make sure we answer all questions related to study design, including from NHANES, if you have any. Any other questions?
Okay. Seems you've answered this one. I still do not understand the difference between PSU and strata and how to account for them in NHANES data. Are we going to have a hands-on application of these?
Okay, so let's say that, okay, let's go back here. So this is our day 2 and analysis, right? This is the data we had yesterday. Let me make this bigger. So once you open the data set, the first thing you're going to see in the Chi-Squares platform is it's going to ask you, would you like to adjust for complex survey design variables, weight, PSU, stratum? Question. You can say yes, you can say no. Every single time you upload data set, even if you say no, right? If you simply just, let's come back to it. Let's go back to our analysis. Again, every time, even if you just refresh the page, we will always display that for you because it's so important. We can't allow you to forget it. And setting those variables is super, super simple, right? Just click yes, and then choose the variables. So you can say your weight variable is weight MEC2. The PSU variable is PSU. How do I know this variable? Well, I read the documentation. So how are you going to know what these variables are? Well, you have to read the documentation too. If it's a survey that you created, well, you have to write the documentation well so that other people can read and understand. So please, you can't be a good researcher or a good scientist if you are not a good documenter. You have to be able to write good documents, technical notes, so that other people can read and understand. Very important. It's not about writing manuscripts only. I know all of you want to be writing manuscripts. Somebody has to also write a technical documentation for other people to read. So PSU and the stratum is the stratum variable. And this is all you have to do. It's that simple. You set the variables and you can now go to sleep, and everything from henceforth, the platform will automatically account for those variables in the complex design in the analysis. You don't have to do any other thing. That is all. That's how it works on the Chi-Squares platform. So when you are designing your studies or setting up things, everything will be accounted for accordingly. Now, these features here also allowed you to be able to come up with an analysis framework in which those weight variables and PSU and strata are automatically accounted for. And take note that this analysis mode automatically changes to weighted once we set those variables. Now, what happens if our data set had no PSU? Well, we don't have to select. It's not a must that you must select all 3. You just select the ones that you have in your data set, right? If our data set only had weight, we'll select only weight. If it had weight and PSU, so as you can see, it's not a requirement to select all 3. You select what you have. If you selected all 3, but you want to do unweighted analysis, you can just say, switch this button off. So the platform knows that, okay, you have weight selected, PSU, and stratum, but for whatever reason, you don't want to apply those variables in your analysis. Again, the platform will still switch to unweighted mode. So you can, this is right here in your face so that you can't forget. You cannot, you can't help but notice all the time, right, that this is the mode I am on. I'm on unweighted. So in this case, if I want to set it back, I just come back here and toggle the switch on and save, and it's back to weighted. So at this point, every analysis on the platform will automatically weight the data. And now one of the challenges in analysis of complex survey data on other platforms is that it becomes very hard for you to account for the commands. The command for setting up, let's say a 2 sample t-test for weighted analysis is quite different from the command on weighted. On the Chi-Squares platform, there's no such thing. Once you set this thing up, any procedure you run will automatically account for the design. Now, the question is, what if you have never written a manuscript, right? Okay, sure, you have set it up. What next do you do? What next can you do? Well, you can come to the analysis wizard here and come to the analysis suggester. That's why you have this button here. New to manuscript writing, well, use the analysis suggester. If you have no clue how to write a manuscript, but you have to write a manuscript, the analysis suggester is your friend. So you just click the analysis suggester, or you can come to it from here, analysis suggester, and you come to this page. This page is asking you to now supply your variables that you care about. There are 4 input fields, 1, 2, 3, and 4. The first one says, choose the single most important outcome variable for your analysis. Again, by the way, this is the enhanced data set we're working with yesterday. So this is a continuation of it. So go back to analysis suggester. So choose the single most important outcome variable for your analysis and specify its type. And you can read the justification here. Here, the justification says, every study needs one main outcome, just like a ship can only have one captain, right? If you have several possible outcomes, choose the most important one as your primary outcome. The others can then be listed as secondary outcomes. Your primary outcome should be a variable that best represents what your study is about, the one you'd mention first if asked for a quick summary. Factors like impact, prevalence, stakeholder interest, and data quality can guide your choice, right? So this is written in a way that is very simple. We don't like complexity at chi-squares. We want things to be expressed simple so that everyone can understand. So here, the bottom line is I just select the most important variable for your analysis. So let's say in this case, my most important variable is, let's say, severe periodontitis. I select that. The platform automatically notes that this is a binary variable. Next, it says I should choose 1 to 15 secondary outcomes. And again, secondary outcomes, what does it say? We also ask you to select at least one secondary outcome. Secondary outcomes add depth, help check whether results are consistent, and strengthen your story. For example, there could be variants of the same outcome. For example, cigar or chewing tobacco use when the primary outcome is cigarette smoking. There could be the same variable outcome variable measured in different ways. For example, self-reported smoking versus biochemically validated smoking. There could be a different but related dimension. For example, tobacco price when the primary outcome is smoking frequency. And there could be some other exploratory outcome which may not be powered for statistical significance, but lays the groundwork for future work. For example, we are measuring time to first cigarette or cigarettes smoked per day among a subset of smokers when the primary outcome is cigarette smoking in the overall population. So in this case, the secondary outcome is among a subset. So when these different measures point in the same direction, we call this coherence, right? So if you look at the primary outcome and the secondary outcomes, all roads should lead to Rome, right? If the results should point in the same direction. And that's what we mean by coherence in study design. So that's why we require you to select 1, 2 outcomes, secondary outcomes. So here, let's say that I select my secondary outcomes as moderate periodontitis and as, let's say, mild periodontitis and as any periodontitis. So these 3, I select those as my secondary outcomes. And then it says choose the main predictor or exposure variable for your analysis. So let's say my main predictor is current smoking from yesterday. I select that as my main predictor variable, and this is an unordered categorical variable. And then lastly, it says choose the main demographic variables or other key covariates in your data set. So I select, for example, education. I select poverty index ratio and age, and let's say sex. And let's say education level, all the variables from yesterday. thought we had. Okay, thought we had education. Let's see. Okay, maybe I didn't create it. And then let's say race. Did you create race? Yes, we had race. So let's say I select all those variables. I can then select the type of variables they are. Okay, education was there already. This is an ordered categorical variable. This is ordered categorical variable. This is ordered categorical variable. This is unordered. And this is unordered. So I have never done any research before, but at least you should be able to select these variables, right? With the guidance provided. So once you're done, all you have to do is click on suggest analysis. So what happens is the platform takes all of the information you've provided and then suggests analysis for you that says, well, based on what you have provided for us, here are possible approaches you could take for your analysis. You should, in this case, it says, here are tables that we have created for your paper based on your selection. Table 1 could be characteristics of a study population, and the justification is provided. It says table 2 could be overall and stratified prevalence estimates of the selected outcomes. Table 3 will be adjusted odds ratios assessing the correlates of the outcome. And table 4 suggests a sensitivity analysis, right? You can always suggest alternative models if you don't like the one. That is if you know what you're doing, right? If you don't know what you're doing, just stick with the suggestions they have provided. Now, for more advanced users, there are also some diagnostics provided here. If you're interested in confounding, right? Confounding is when we have a variable that is associated with both the exposure and with the outcome, but does not lie on the causal pathway. So the question is, I'm interested in the relationship between smoking and severe periodontitis. So which variables in all of the variables I have selected are potential confounders? Well, you don't have to, the platform does all of that for you automatically. You don't have to start doing it manually. All you need to do is click on the button, confounding variables, and the platform takes that information and assesses for confounders for you, which is what it's doing now. So you have a definition of a confounder. If a confounder is a variable that is related to both the exposure and the outcome, but it's not part of a causal chain between them, it is important to identify and include all confounders in your analysis. So of all the variables that I selected, at the threshold of P0.2, these are the confounders that I identified: education, poverty index ratio, sex, and race. When we are assessing for confounders, we don't usually use the 0.05 threshold. We use a much bigger threshold so that it allows us to identify confounders, right? You can always change this threshold. You can say, well, I don't want to use 0.2. I want to use, let's say, 0.1. Well, the platform will reassess the confounders and say, well, at this threshold, these are the variables that are deemed to be confounders based on the epidemiological meaning of a confounder, right? And it will then tell us what those confounders are at this threshold. You can also view the results from bivariate analysis, right? It's not just pulling the numbers from the air. It's actually calculating beneath the scenes the relationships in the bivariate analysis, and that is what informs the information displayed to you here as confounders. So let's look at the results quickly. So here, so remember that confounding is a two-test benchmark. Is this variable associated with the exposure, and is it associated with the outcome? You need to be associated with both exposure and outcome, and also not lie on a causal pathway, obviously, for you to be confounder. So the platform tests for association with the outcome. It does all of these tests in the background, and here you have the variables, independent. The platform obviously knows the kind of test that needs to be done based on the type of variable that is there through a decision algorithm, and it performs those tests. You have the p-values. So this is the first part of the test, association with outcome, association with the exposure, and you have this. So on the basis of these variables that are associated with both the outcome and the exposure are deemed to be confounders based on an epidemiological meaning, right? So that's how the platform allows you to be able to make those decisions without having to bang your head on the wall. The same thing applies with collinearity. The platform also helps you assess for collinearity. And so again, the point is so that you have, empowered decision making. Decision making has to be based on knowledge. And so even if you don't know how to run those tests, those are run automatically for you. And so you don't have to, at least you are well informed. So here, these are the correlations between, for example, the different variables. The platform captures this by means of the R squared or adjusted R squared. The adjusted R squared simply tells us what part of the variance for this variable is explained by this variable. If A explains almost all of B, that means that they're very correlated, right? So that means that they may be collinear variables. So for example, we see 17.6% of the, of the variation in education is explained by poverty index ratio. So that you can see that that's the highest correlation measured here. So it's like, okay, well, there's definitely a correlation between poverty and education, but it doesn't rise to the point where we will call it severe collinearity, right? And so, yeah, this is just here to help you too with your variable choices. If you selected variables that were very collinear, well, you're going to see a red flag, and that will tell you, well, maybe you should consider, right? So those are some of the features there on the platform to help you when you're selecting variables, such that even if you have never done analysis before, even if you have no clue what you're doing, the platform guides you to make the appropriate decisions. So that when you run your analysis, when you click on run analysis, all of this analysis automatically accounts for the survey design. You don't have to say, oh man, okay, now I have to. No, the platform automatically accounts for the design in all of the analysis so that you don't have to do anything extra, right? So by just clicking estimate, the platform takes the weight variable, takes the PSU variable, the stratum variable, and accounts for them in the analysis. So in this case, here we have the table 1, table 2, the table we've just created. This is the demographic table. You have a plot, you have the text also generated by the platform, and this is weighted. So if you look at the metadata here, you see the analysis, population characteristics, denominator, but then you see weighting, true. The platform has automatically taken the data and has automatically accounted for all the complex design. You don't have to do anything in addition. It's already done in the background. So all you need to do is now you can push the results to your manuscript, right? So that's that. I don't necessarily want to go into the details of manuscript writing today. Just to show you how the platform automatically accounts for this when you set up your manuscript and you're writing. So your focus is not really on, the technical details. You just worry about the message you want to craft from the manuscript. You don't have to worry about, geez, how am I going to account for weights? Geez, this PSU, how is it done? No. You set the variables and the platform takes care of everything from that point. So I hope that is clear to the person who asked that question. Any other questions?
Ilya, I see a question. Okay. We're using the Multiple Indicator Cluster Survey 2021 from UNICEF to assess vaccine hesitancy and its impact on childhood immunization coverage in rural northern Nigeria. But the dataset covers all the states in Nigeria. To accurately address this topic, we will need to merge 3 datasets. However, we only want to include a few variables from 2 of the datasets. Does the chi-squares platform allow users to select the variables they want to include while merging datasets?
You can merge dataset, but you don't have to use the variables in the merge dataset. But I mean, something in the earlier part of the question caught my attention. It said the survey covers all the country, but you're only interested in northern Nigeria. So in that case, when you're doing your analysis, what you need to do is do a subset analysis. You can't drop rows. So first of all, remember we said the framework yesterday that you can never drop rows. You can't just go into Excel and delete everybody who is not from northern Nigeria and say, oh, okay, now I have my clean data set. No, that's completely wrong. You have to come and use subsets. So here you could come here and you define the subset. You say, all right, My analysis is based on, let's say, people who are aged, let's say, let's assume that this is the variable for Northern Nigeria, right? You say, let me use, I'm just using a random variable here. This variable, like, you set the value for what is deemed to be eligible. So in this case, let's say my analysis is among individuals with this value greater than or equal to, let's say, 30, right? So in this case, or in your case, if they, if the state variable contains any of the following states, Bauchi and Sokoto and whatever, right? And then you can set the subset. You can always check the sample size to see how many people are eligible based on this criteria. And it doesn't have to be a single variable. You can add many variables. You can say, okay, that variable, or for example, this variable, right? So in other words, I'm saying if the value of this variable is greater than or equal to 30, and the value of this is exactly equal to 1, for example, and then I can check the sample size again. In this case, of course, I will expect it to drop down. So this is what you need to do. In the background, what the computer is doing is that it is estimating the variance and the point estimates correctly. The point estimate will always be estimated only among these individuals, but the variance must be calculated among everybody. Otherwise, your calculation is wrong, right? Because you have incorrectly estimated variance. So please do not ever drop rows. Don't say, oh, my population is only among Northern Nigerians, so I have to delete the rows for people who are from Southern Nigeria or Western Nigeria. That is a no, that is a hard no. You can't do that. You need to use software that accounts for complex survey design, right? Chi-Square's platform does that. You can also use R or whichever software that you use, but just that in the Chi-Square's platform is much easier to do that because it's designed to, so you don't worry about the technical details. We have the technical details covered. You just worry about what message you want to cover, and that allows you to then, generate a paper that actually has impact instead of just worrying about fixing bugs. All right, so that's how you're going to do it.
Thanks, Prof. Is it possible to provide written feedback on the questions, the homework questions, to keep us as gold standard? To keep with us as gold standard?
Yeah, you can provide written information. You can drop them as comments. I love to read your comments. Nobody ever writes, but when you write, I like reading it. And yeah, so you can email it, you can drop it in the, yeah, you can share your comments so that other people can also benefit. So yeah, you can, I think it's now LinkedIn feed, so you can always provide written comments. And I think for yourself, it's also always very good. I think that the process of writing things down really solidifies it, right? So if you go through the homework and you write it down, preferably with a case study, that helps solidify things. Like, we all are methodologists, right? If you're doing research, you ought to be methodologists, and the goal is to completely eliminate this situation where you take your data and you give it to somebody and say, hey, analyze my data, or hey, design my study for me. Like, no, we shouldn't be doing that, right? We need to own our craft as methodologists, because that's the only way we can understand what we're doing and be able to interpret our results correctly.
Thank you. My question is related to the last person question on sample size. My population is 151,553, and I chose 400 as sample size, but the panel complains it's too small for students and lecturers.
The panel complained that it is too small. Well, did the panel provide any justification for why it is too small? It's a question of what the outcome was, and so you can educate the panel on why it is not too small. You can perhaps show them what went into the formula, and you can perhaps ask them what will they change. Politely tell them to stop being armchair critics. Maybe you shouldn't tell them that. But you can provide more credible evidence of what you did, right? So in this case, for example, let's leave this part and let's go to sample size. So you go to data collection, sample size. So in this case, you said your study, I'm going to assume it's a survey. Please correct me if I'm wrong. Your population size is 150,000. And let's say the of the outcome is 50%. We're doing a simple random sample. The margin of error is 5. Maybe we anticipate a response rate of 50%, 50-50. Obviously, the sample size we get will be a function of the parameters that we put in here, right? So without knowing what you put in, maybe the supervisors are correct, right? If these are the parameters you put in. But if you assume that, well, I am providing incentives, right? Sample size is not a magic number. It is a very educated guess based on what we think might happen. Things hardly go the way we think they will happen, right? So that's number one. The world was not designed for us, so for our wishes. So the world, who was this boxer now? Mike Tyson said everybody has a plan until they get punched in the teeth, right? So that's exactly what happens. Now you might think, okay, response rate is 75%. And you think that, oh, I'm giving incentives or I have put in a lot of plans to engage this audience. So I expect that I'm going to get high response rate. Well, the sample size drops to 513%. Sorry, 513 individuals. Or you say, well, I'm willing to accept a higher margin of error. The margin of error simply means half the width of your confidence interval. So margin of error of 5 means that I am willing to accept that my confidence interval will be 10 points wide. But let's say I'm like, okay, well, I am fine with accepting a slightly larger confidence interval of, let's say, 7 as my margin of error instead of 5. Of course, my sample size is going to drop to this, right? So it's all about what assumptions went into your formula, right? The devil is always in the details. So it's not enough for you to say, well, Mr. Committee, this is what I calculated. Every sample size you have should have a table. You should have a table that gives you, for example, you can say, for example, response rate, margin of error, and then you have, trial 1 or calculation 1. So this is what you should do as good practice. Calculation 1, calculation 2, calculation 3, and so on. So you can then say, if I assume a response rate of 75% and a margin of error of 5, here's my sample size, right? Expected sample size. I can put other things, right? But I'm just giving you an example here. Expected sample size. So my sample size is 750. If I assume calculation 2, if I assume a response rate of 50, which is more reasonable, and the margin of error of, let's say, whatever, 55%, here's what I will get. Maybe it's whatever it is I'm going to get, right? I'm going to get whatever number is. So you should always present your sample size not as a single number, as 400. It's like, okay, how did you get that number? You should present it as a table of plausible options. So the committee looks at it and says, okay, I see that you are assuming that you are going to have a response rate of 75%. Why are you so optimistic about that? And then you can defend your choice and say, well, I think I'm putting in incentives. I know these guys very well. I've done a lot of work. I've gotten community buy-in. So I think that's how it should be. So please don't just provide a number. Don't fling a number at the committee and say, all right, this is my sample size. This is like, okay, how? So always present a table like this with your assumptions clearly stated out so that everybody can challenge your assumptions and say, well, we disagree. We don't think that is reasonable. And so it becomes a respectful exchange between both parties, fully informed of the underlying assumptions that went into it. Now, if you do this and the committee is still saying, well, we don't agree, well, then you can ask them, so what do you guys want me to do, right? But this is what you should definitely aspire to do. This is what you should actually do, not just aspire. You should actually do this. not this. All right, any other questions?
Thank you, Prof, for the teaching so far. Please, can you suggest the variables that can be used for a retrospective study of a clinical data? Number one, and then number two, is it necessary to collect lab data when doing epidemiological studies?
Okay, it is impossible for me to suggest variables for a clinical study when I don't know the research question. That's it's oh, please mute. All right, as an investigator, it's your job to sit down and say, is the exposure? Here's my exposure. That's where it starts. Here's my outcome. Now, based on the exposure and outcome, you can now say, all right, here are my confounders or potential confounders, which are variables associated with exposure and outcome. This is what study design means. So please let us not outsource our design or the thinking part of the process, right? You need to sit down and come up with a list of variables, right? And then you can now think through, okay, why do I think this is a confounder? So it's a lot of intellectual work. So no one can nor should be able to tell you that, well, here is just a rough idea. This is a clinical study, and so here are the variables. Because the immediate question is, what is the exposure and what is the outcome? That's where we start, right? You should know at least this and this. And then you should now come up with a list of this confounders. And then it's now easier to say, well, I think that you have omitted key variables that are confounders, right? And then we challenge those assumptions of yours. So this is the first step you need to go and sit down and create. The exposure, the outcome, and your confounders at the very least. And then we'll start saying, okay, here is where we can go next. All right.
Thank you. I'm undertaking a cluster randomized control trial in 4 clusters of school in Ghana. My challenge is with sample size difference in various cluster of schools. How do I ensure the sample size is not biased? Thank you.
Okay, sample sizes cannot be biased. They can either be, adequate or inadequate. So the KNHANES platform allows you to calculate a sample size with cluster randomized trials, right? And so let's say your study has 2 arms or 3 arms, as whatever the case might be. What you would have to worry about is the design effect. The design effect is a function of the size of the clusters and the degree of correlation within the clusters, right? We have different ways of estimating it depending on whether or not the clusters are assumed to be of equal size or of unequal size. So, that's why we try to make this as easy as possible in terms of the layout of the UI, the interface, so that it's not asking for too much. Now, if you don't know what all of those things, well, you may just have to err on the side of caution and put a higher value. In general, design effects of 2 or 3 will be sufficient, right? Again, remember that sample size is not a magic number. It is an estimate based on what we think it is the case. So in this case, you can say, oh, well, I'm going to look at design effects of 2 and compare that with 3 and compare that with 4 and see what the sample size looks like. Again, remember, always calculate your sample size as a table like this, right? So here you're going to have design effects as one of those variables. So design effects. So design effects, okay, I'm going to say I'll assume 1.5. Design effect cannot be less than 1 in this case. A design effect of 1 means it's a simple random survey. And since we're having clustering, the design effect is what punishes the clusters for being correlated. It has to be bigger than 1. So I can say, okay, I'm estimating my sample size. This is when you don't know what its actual value is. Well, sample size is all about guesstimating, like making an educated guess, right? No one ever knows. No one ever calculates a perfect sample size. So you can go to sleep at night knowing that you don't have to worry about that too much. So I can say 1.5, 2, 2.5, 3, 3.5, 4, right? Amongst other variables, and see how does my sample size change with this varying assumptions. At the end of the day, it becomes an issue of logistics, right? When we talk about study design, we are always talking about science and variance and all the scientific things. We don't talk enough about logistics and costs, right? Those are also extremely important in study design. You can do all the sample size calculation you want, but if you don't have the money, well, it's dead on arrival, right? So at the end of the day, after all of this is said and done, and of course, this the power, right? You also must include the power in this case. Then you make sure that, all right, I'm going to just stick with let's say power of 80%, and I will just pick this one that I can afford. The trade-off is that I know that I may be more just more likely to commit a type 1 error if I underestimate the design effect. And I'm going to put that in my limitations, right? This is why we have limitation section in the manuscript. So what is required of you in this case is to know, one, the direction and magnitude of the bias, right? You should be able to know, well, if I underestimated this, this is what will happen. And this is the direction where the result will go. That's what we expect of you, right? You shouldn't just say, oh, well, I don't know. I'm just going to pick a number. I don't even know what the impact of this number is, but I'll just pick a number, right? That is not science. That's not methodology. You have to know, all right, if I underestimated this, this is what the impact will be. And the direction of this, impact will be in this direction in terms of quantifying. And you should be able to be very transparent with that in your methodology on your limitations. All right, any other question? I think we're at time now.
Okay, last question. Maybe second last. Is it right to add 30% on top of every sample size?
Well, I'm not sure where you got that, but sure, if you want to add, that's conservative. But if I were an ethics board, I will ask you why. Why are you doing that? Is it required? Because if every study has harms, and why do you want to expose 30 more people to just some harm if there's no legitimate basis for it? So we should be able, as scientists, we should make sure that whatever we do is defensible. It's not just that, oh, we read somewhere that people do this. No. It's all about context. Why are you doing it in your context, right? So for everything you do, there should be some defensible reason for doing it. So if an ethics board asks you why, you should be able to, or your supervisor asks you why, you must give a cogent answer that is reflective of your context, not that I heard that people do this. No, that's not an acceptable answer. I am doing this because XYZ, right? So, it's not customary, but if there's, I'm not sure there may be a reason, there must be a reason why you're doing that. But again, just make sure it's defensible.
All right. Thank you.
Right.
Okay, and last question.
This is your last question.
Asking for a friend. He's doing a panel study to assess how methane gas and PM and weather conditions affect respiratory diseases among waste pickers. He's asking how to calculate his sample size. Does he necessarily need a comparison group for such a study?
Well, so he says it's a panel study. Panel study, people use that word very loosely. It's almost like a colloquial term. So we need to first of all understand what the person means by panel study. Is it a cohort study, right? If it's cohort study where you have exposed and non-exposed individuals, so a cohort study is where we have, let's say, in this case, for example, he's talking about garbage pickers, right? So it could be that, well, we're trying to look at, the risk of this disease among garbage pickers compared to other, an adjacent, another occupation that is not exposed to garbage, right? So we start off with people who are disease-free, and we'll follow them over time to see which of these two groups has higher rates of the disease. Well, that's a cohort study, right? So I don't know what the study design is. Again, remember,
It's a cohort.
Hmm?
The last message is cohort
Well,
study.
so if it's a cohort study, well, then you need a control group, right? So if you are calculating sample size for comparative study with 2 arms, with percentage as outcome, you select a prospective cohort study. Well, you have to provide the prevalence of the outcome among a non-exposed group, which is the population that is not picking garbage. And then you can now pick a quantity below. You can say, okay, I expect, and the prevalence, I think that the prevalence of this outcome. So let's say that you are thinking of, let's say, a lung disease. You say that, well, in the non-exposed group, the prevalence is like 20%, but I think that the prevalence of this outcome among this group will be like 15%, 35%, 15 percentage points higher. I think that I want to express this at the 95% level. This is going to be a 2-sided test. I don't know where the direction will be, but I'm open to going any direction. I want to test at 90% power, and my response rate is this, right? So in this case, the platform tells you that, well, you need 249 individuals among the exposed group, which are the garbage pickers, and 249 among the non-exposed. So your total sample size in this case is 498 individuals, right? So a cohort study is an analytic study, which means you have a comparison group. And so, yeah, you need that number of people based on these assumptions provided here.
Thank you. Thank you, Prof. That was the last question.
Okay, last. All right.
We can get you more if you want.
No, please. I think that's a good place to stop. That is so funny. All right. So
thank you very much
for coming up, and I hope you learn 1 or 2 things from about analysis of not just enhanced data in particular, but generalized to complex surveys in general, right? Including the principles and philosophy involved in not just the analysis, but also their design. All right, we're going to announce our next class, and we hope to see you there too. So thanks, everyone, and look forward to seeing you shortly. And please do your homework. We'd like to read your comments. All right, bye.
Thank you.
All right, cheers, bye.
Thanks, everyone, for joining.
I am the genie of the academic lamp. I shall grant you 3 wishes. Great. For my first wish, I want to be the most handsome man in the world. Bro, I'm a genie, not a god. You need prayers for that. Fine. Then for my second wish, give me a 6-pack. 6-pack? Gym, discipline, pain, prayers and prayers, sorrows and sorrows. What kind of fake-ass genie are you? All right, third wish. Write my entire paper for me, beginning to end. It's due Monday. If I don't submit, I don't graduate. That I can do. Head over to Chi-Square's platform. It's built for researchers like you. No AI gimmicks, just real automation. Data, analysis, writing, referencing, all in one place. Your paper, in a weekend, no magic lamp needed. Chi-Squares. It's like magic, but real.